Alright, so let's look at some examples of code where we make use of the struct data type, right. Now as explained earlier, basically what I have done over here is I have declared a certain struct, right. So there is a struct fruit and I mentioned the char star name, int quantity and float price, and you will notice there are two things you can notice over here. The first is where have I declared it, right. It is not inside a function. This is in what is called the global scope or the file scope, which means that this particular declaration that I see over here is visible throughout this file. Any function that is present in this file can make use of this data type from here onwards. And it kind of becomes interesting to know why, right. We will take a look at an example of that later. Now you will notice also that I have just declared struct fruit and ended it with a semicolon. There are no actual variables of this data type assigned over here, right. But the next thing is I have a function and inside that function I now declare it as struct fruit apples, and it is able to, the compiler is now able to pick up that this struct fruit corresponds to this struct fruit that I had declared out here, right. They are the same data type. So struct fruit apples has now been defined on line 10. And I can now go ahead and start assigning to the fields. The notation that we use for assignment is the variable name, that is the struct name, dot the individual field names, right. And you will see of course that Replit and a lot of reasonably good code editors will make things a lot easier for you. The moment you sort of keep your mouse over one of the parameters, it shows you that apples is of type struct fruit and name is of type char star. You will also see that the name itself has been denoted as star fruit : name, right. And this : notation is actually more from C++, not really from C, but basically what it is saying is something called a namespace, right. It is telling you that the name, the variable name, somewhat unfortunately named over here, so let us look at quantity instead, right. Quantity, in other words, is something that belongs in the namespace of fruit. In other words, it is a sub data element of the data type fruit. Okay, that is one way of looking at it. Okay. So you can see that I can now assign apples.name equals the string apple within double quotes, right. And what happens when I declare something like this, right, is that automatically the compiler takes this particular string apple, puts it somewhere in memory, as I said, the constant data corresponding to this program, make sure that the byte immediately after the E over here is a 0, so that the string is properly null terminated, takes a pointer to the character A, which is the first character of the string, and puts that into apples.name. Apples.quantity is a lot simpler. It just takes the integer 10 and puts it into the location corresponding to apples.quantity, right. Now what that effectively means, and the way to think about this is, the moment I have declared struct fruit apples, the compiler has set aside some memory in the memory of assigned to this program that is enough to store all of these quantities, right, the char star name, the int quantity and the float price. Okay, all of these quantities can now be present. Each of them is individually a variable, which means that in some sense it is an alias or a pointer to some location in memory that stores a certain value, right. So it is possible, for example, to take the address of apples.quantity and the address of apples.price and so on. Okay. Alright, so now how do I use this, right? I have assigned values to it. How do I use it? Well, I can use a printf statement like this. There are %d of type %s costing %f each, apples.quantity, apples.name and apples.price. Okay. So let us see what happens when I run this. It goes ahead, compiles it and prints out the message saying there are 10 of type apple costing 25.900 each, right. And of course this printing out the %f, I have not specified how many digits to print and so on, so it just goes ahead and uses its default notation, which ends up giving me a lot of probably unnecessary decimal places, right, but it is okay. It is readable and understandable. Alright, so now we know how to declare a struct, how to assign values inside a struct, and also how to use the quantities or how to use the elements that are present inside the struct. Okay. There are a certain other kinds of notation also that are present here, right. So, for example, I could try something like this, right, struct fruit bananas equals, and directly try to assign something of this sort, right. And let us see what happens when we run this. So, what has happened over here is I have declared struct fruit bananas and I immediately initialize it, right, and the initialization has happened using this curly bracket notation, right, and what it does is that it picks up the first element banana, creates a string corresponding to it, it takes a pointer to the first element and assigns it to the first element out here, that is the name, right. It then takes this 15 as an int, assigns it to the quantity, takes 30.0 as float and assigns it to the price. Okay. So, bananas in other words has automatically got the three things just because they were given in the correct order, right, and as you can see it printed out the value properly out here. Okay. There is one more way of doing it, which is to say that I could now do something like this. I can assign struct fruit mangoes. Now, you will notice over here that the first thing I have done is assign the price, right, and the second thing is the name, but the way that I have done it is within the curly brackets I actually said dot price equals dot name equals and so on. So, this is effectively what is called named arguments, right. What we have over here on line 19 is what we would call positional arguments, that is just based on the position I know that the first position element banana is a string and therefore the char star of that should be assigned into name. But over here I am giving it the parameter to which it is to be assigned. I am saying that the price should be set to 12.5, the name should be set to the string mango and the quantity should be set to 5. Does that work? Sure enough, we get the correct result from there as well. Okay. So, these are three different ways by which we can declare and initialize a set of parameters out here or a set of, or a struct, the values corresponding to a struct. Okay. Now, one thing over here is, does this notation work, right? So, if I try directly later on, I have already assigned bananas out here. Now, I would like to assign a new set of values to it. I want to change the name out here. Now, of course, there are two ways. I could always give bananas dot name equals and so on, but I want to directly try and do something like bananas equals this, and you will see that even the compiler right here is giving me an error, right. If I try running it, I basically get an error saying expected an expression. Now, what does that mean? It looks as though I am doing it exactly the same way as I had on line 19, right. There is really no difference between line 19 and this notation on line 28, except for the fact that line 19 also had a definition, what is bananas being defined as. Okay. So, this does not work. On the other hand, if I replace line 28 with this, right, an explicit typecast, right, and then try doing this, then I find that it's running and yeah, it's able to run, right. What happens is this updated assignment on line 29 basically was able to change the banana to type B, right, the name of the fruit was changed to B. The other parameters remained the same, well, not exactly, okay, even those changed, they became 20 and 15 respectively, right. So, all of those parameters got updated, right. So, in other words, typecasting solves the problem that we had on line 28. In line 28, for whatever reason, the compiler decided that it did not know what we were trying to do, but the moment that we explicitly gave a typecast saying think of it as a struct fruit, the compiler was able to figure out what we wanted to do with it, right. Now, this is, if you think about it, a quirk of the compiler, right. You could argue that after all I have declared bananas as type struct fruit, so why couldn't the compiler figure out that I was trying to assign the values into the struct fruit? That is a decision that was taken by the compiler writers, right. Their are probably reasons why it is non-trivial to do such a thing in general, right. In this case it might look very trivial, but in other kinds of structs there could be problems. The bottom line is you cannot always assume that it will work, right. On the other hand, typecasting does work. And of course, if we leave all that aside and directly try assigning a certain value bananas.name equals b, that should work, of course. And interestingly enough, what will happen in such a scenario is that it retains the old value of the quantity as well as the price. You can see that from the original value was set for banana as quantity 15 and price 30. Now the only thing that has changed is the name b. The quantity 15 and the price 30 remain as such, right. So it's possible to change just one element of the name of a struct parameter without necessarily having to change everything in it. Alright, so now let's look at how we can find out a little bit about the size of a given struct and understand a little bit more about how these things get arranged in memory, right. So we have the same struct as before, and interestingly enough you will notice that I have sort of redeclared it over here, right. I still have this global declaration out here of struct fruit starting on line 3. I also have another declaration of struct fruit starting on line 36. Now we will look at this later, but the bottom line is this actually corresponds to a locally scoped declaration, right. So this struct fruit exists only inside this function, right, and right now it does not matter to us. What we can do is we can declare a struct fruit apples, and now if I run this, right, it should print out the size of the struct fruit and it should also print out size of apples, and in both cases we can see that the answer is 16. Now let us try and understand why, right. What we have over here is that the first element of fruit is of type char star. This is a 64-bit machine. The processor is a 64-bit processor. So char star is an 8-byte value, a 64-bit value. So the char star is occupying 8 bytes. Int is a 32-bit value, 4 bytes. Float is another 32-bit value, another 4 bytes. So it makes sense that the size of the struct is 16 bytes, right. After all, size of gives us the parameter, the result in bytes. And as expected, the size of struct fruit and the size of apples are exactly the same, right. But let us look at a slightly different and a bit more complicated struct in order to understand potential differences out here. So I have declared a new data type that I am just calling dummy, which has a number of different parameters, right. It has a character A, not a character, not a char star, short b, int c, float d and double e, right. And you will notice that along with declaring this struct, I am also declaring element x which is of that type, okay. So that is fine. What we can do is print out the size of x and also look at the individual elements present inside x, right. What is the size of x dot a and size of x dot b, right. Now let us first, before we look at the results, let us think about whether we can sort of estimate what we expect to see out here. A char, as per our understanding, is of size 1 byte. So at least size of x dot a should come out as 1. Short is supposed to be 2 bytes, size of x dot b should come out as 2, okay. Which means that in principle I should hopefully expect to see something like 1 byte for char A, 2 bytes for short b, so that is 3, int c is another 4 bytes, 7, float d is another 4 bytes, 11, and double is 8 bytes. So total of 19 bytes is what I would expect to see. Let us check if we actually get the size of the struct as 19. No, we get 24, right. So now let us think of it in the context of the packing that we talked about earlier, right. Why might this actually be happening? We know for sure that the double is going to end up taking 8 bytes, float is going to end up taking 4 bytes, int is going to end up taking 4 bytes. So we have a total of 16 already accounted for over here. We wanted another 3 bytes to store these two parameters, but what it looks like is they are taking 8 bytes, probably looks like around another 4 bytes each, right? And the question then becomes why, right? In order to understand that, one way of looking at it would be to actually look at the individual addresses of the elements that we have present out here, right? We can take the address of x, we can take the address of x dot a, x dot b, and so on, all these parameters, right? And let's run this and see what happens. Now what you can see is that the address of x is some large number once again, right? Keep in mind that these are some 64-bit internal addresses. They are not even the physical address actually present in the memory. It is something called a virtual address that is assigned by the operating system. So the number by itself does not matter. Every time you run it, it will change. What does matter is the relative offsets that we are talking about, right? So what we have out here is, I can see that this first number, look at just at the last few digits, right? The 7552 corresponds to the address of x. In other words, the entire struct dummy has been declared starting at address something 7552. And now look at the address of a, right? X dot a. It turns out it is exactly the same as the address of x itself. In other words, the first parameter, the first field inside a struct essentially corresponds to the beginning of the struct, right? So the pointer to the struct and the pointer to the first field of the struct are the same address, right? This is actually pretty consistent as part of how the C compiler works, right? There are in fact certain kinds of code that even make use of this, right? They make use of the fact that the pointer to the struct and the pointer to the first field of the struct are the same address. However, that is not really logically something that you should rely on, right? It is most likely going to be true, right? But it's confusing in most cases. The reason why it sometimes gets used is it allows you to write code which sort of mimics the behavior of object oriented code, right, or classes in certain sense, but at the cost of understandability, because you have to sort of know that these two pointers are going to be the same and then make use of that, and it's not at all something that is obvious from just thinking about how a struct would work, because it's entirely possible to think about a compiler as having some additional metadata, something about the struct present as the first few bytes before the actual fields begin. It turns out that in C it does not do something of that sort, but it can make things confusing. It's strongly suggested don't rely on that kind of code, okay. But as we can see in this case, at least, it turns out that the pointer to the struct itself and the pointer to the address of the first element in the struct are exactly the same, 7552. Now I would have liked the short to start at address 7553, but remember a short is 2 bytes, right? So it needs to be 2 byte aligned, right, which means what that means is that the address of the short has to be a multiple of 2, right, and that's what ends up happening out here, right. It basically takes this value, right, and rather than making it 7553, it makes it 7554 so that it becomes a multiple of 2, and the reason for that is it makes it easier for the processor to pull out a set of 2 bytes directly from memory, okay. So now what we can see is that 2 bytes have been used up for the char and another 2 bytes have been used up for the short b, okay. Now what about x dot c, right? What we can see over here is that the address of x dot c is just another 2 bytes from there. C is of type integer. I want the address corresponding to C to be a multiple of 4, and sure enough 7556 is actually a multiple of 4, so that's not really a problem, right. So I can go ahead and use it. Similarly, float is D is of type float. I want that also to be a multiple of 4, and it turns out I can use the address 7560 for that. Now comes the interesting thing. I have the fifth element E, which is of type double, right. I would have thought that the address starting at 64 would be okay, But it turns out that this big number ending with 7564 is actually not a multiple of 8. To get to the nearest multiple of 8, I need to go to 7568. So effectively, in other words, 4 bytes after D are wasted. I simply do not have any valid data present over there, right. What the compiler has done is it has padded it out with 4 bytes that could be zeros, they could be nulls, it does not really guarantee anything about how they are going to be, and in fact it does not even guarantee anything about exactly how many bytes are going to be there. One compiler might choose to align it in this way, but that does not guarantee that all C compilers are going to do exactly the same alignment, right. So like I said, do not rely on the fact that this kind of alignment is going to happen, but if you do look at it, you might find that the number of bytes used by the struct is more than you expected, and the reason for that is this double out here needs to be 8 byte aligned. I need to have its address as a multiple of 8. So it chooses the nearest multiple of 8 greater than 7560, turns out that is 7568, and uses that as a starting point for the double value, which is E. Okay. So what happens as a result is that something which should have taken 19 bytes ends up taking 24. Okay. It can get worse. Let us look at what happens if I just sort of change this around a little bit, right. I am going to just move this int C into the second place after the char A, and I am also going to try and move this double E into a different location. Okay. The parameters are actually exactly the same, right, their names are the same. So in other words, if I take this dummy and if I had another dummy that was declared somewhere else and I assign the two together, they should sort of point by point match. There are other reasons why they won't exactly match. I'll need to actually have the same type definition as such, but at least as far as the parameters are concerned, this is exactly the same, right. The declaration, the order of declaration of different parameters should not affect the functionality of the code, and in fact it does not affect the functionality. What it does affect is the size occupied by the struct itself, right. And when we run this, we find that now the size of struct dummy is 32 bytes. Why is that? Let us go look at it again. What we find is this struct, the pointer corresponding to x is at this value 688, right, and that is also the address of char A, right, 688. Okay. Now the interesting thing is I would like to go directly to 689, right, and no, that does not really give me something that is byte aligned, right. So or rather int aligned, which is a 4 byte aligned. So it ends up going actually all the way up to 696, right. Now that is a bit surprising. Why would I not just go to 692? That is probably related to how the rest of the alignment also works in this case, right. And in fact in fact it is at 692, my mistake, right. So C, it is just that the order in which I am printing these out has got reversed. C has actually gone to location 692. B, which has moved below C now, has gone to 696, right. So that sort of makes sense. Basically what we are saying is that the char A, right, started at 688, 689 would have been a potential location for this int C, right, except that it is not a multiple of 4. So I go to the nearest multiple of 4 and find that it is at 692. After that I then go to a short B. I need 2 bytes for this, I need a 2 byte alignment. I can go to 96, and yes, that is a multiple of 2, so that is not a problem, I can use that for B. The next value is double, it has to be a multiple of 8. So 2 bytes from 96 would have been 98, that is not a multiple of 8. Another 2 bytes would have taken me to 700, which unfortunately is also not a multiple of 8, right. I need to go to 704 out here in order to get to a multiple of 8, right. So a lot of bytes have suddenly got wasted in the middle, right. And finally after that I find that the float D, I need a multiple of 4, and yes, I started off with 704, which is a multiple of 8, stored 8 bytes, got to 712, it's also a multiple of 8, which automatically means it's a multiple of 4. So this is okay. But as you can see, the number of bytes taken by the struct has changed. What did I do? The only thing I did was change the order in which certain things were declared, right? And effectively what has happened is this, there's a 33% wastage of space, right? Because in fact it's more than that, because the actual number of bytes is only 19. I was previously using 24 bytes, now I am using 32, so the wastage of space in some sense has increased quite dramatically, right? And this is something that can potentially be problematic, right, if you have a lot of different sized fields present inside a struct, right. In most cases, unless you are really trying to optimize your code for performance or for memory usage, this is not something that you pay attention to right at the beginning, right. The readability, understandability, maintainability of the code are probably more important to start with, but this can hit you when you actually come to performance at some point.